Welcome back to Neural Intel. Today, we're getting physical. We're going to break down a really strategic roadmap for the next couple of decades in robotics. We're taking this kind of sci-fi idea of android dreams and turning it into a hardcore technical plan for achieving what's known as embodied general intelligence.
Let's kick things off with this idea, because it really frames the entire challenge ahead. The danger isn't that robots are going to disobey us. It's that they'll obey perfectly. Think about that. For anyone looking to deploy this stuff in the real world, the engineering stakes are just astronomically high. Perfect obedience requires perfect programming, and that's a whole other level of difficulty. So what's the grand prize in this whole race? It's something called embodied general intelligence, EGI for short. And yeah, this is the big one. It's the next leap. We're not just talking about AI that can write an email. We're talking about AI that can build the desk the email is written on, AI that can actually do things in the physical world. And believe it or not, the technical roadmap to get there is starting to look surprisingly clear.
Okay, so what is EGI really? Well, unlike a large language model that just chills in the digital world, EGI is all about mastering the physical one. It's about understanding physics, cause and effect, and actually interacting with stuff. Learning, reasoning, and doing. So, to really get how we're going to build this, we have to start with the single biggest problem standing in the way.
And that problem, the first and most critical hurdle, is data. It's always data, isn't it? But for robotics, it's a completely different beast than what LLMs had to deal with. See, language models got to train on basically the entire internet. But data about physical actions in the real world, that's a whole lot harder to come by.
Yeah, this slide really just nails it, doesn't it? LLMs were built swimming in an ocean of data, all the text and images on the internet. Robotics, on the other hand, is basically stuck wandering in a data desert. And I'm not exaggerating. The biggest action data set we have is less than 0.01%. That's 1 to 10 thousandths of what a frontier LLM trains on. It's a rounding error. You just can't scrape the real world like you can a website.
So, this massive data shortage forced the first big strategic move in the race. It was basically a brute force approach. The thinking was, okay, if we can't find the data, we're just going to have to make it, one painstaking, robot-controlled action at a time.
And the core tech here is something called a Vision Language Action Model, or VLA. You can basically think of it as an LLM for robots. It takes in video and language commands and spits out physical actions. So to get the data to train these things, companies, like our fictional example Waytech, used a technique called teleoperation. That's literally having a human drive the robot remotely, like a high-tech puppet. It's incredibly slow, but it generates perfect, high-quality data for one very specific job.
And this playbook led to the first really viable business model in the space, Robots as a Service, or RaaS. I mean, let's be clear, this is not general intelligence, not even close. But for a simple, high-volume job like sorting packages in a warehouse, it absolutely works. You just brute force the data collection, train your model to imitate the human, deploy a whole fleet of these things, and then you sell that automated labor by the hour. Simple, effective, and profitable.
And it works really well. I mean, we're talking about a potential $10 billion a year business just by automating a handful of these narrow tasks. So for anyone in enterprise, that's a huge takeaway. You do not need to solve EGI to build a massive business. But, and this is a big but, this strategy has a hard ceiling. It's a dead end. You can't teleoperate your way to general intelligence. It just doesn't scale.
Right, so that teleoperation playbook hits a wall. You just can't scale it to cover all the things humans do. It would be insanely expensive and logistically a nightmare. So this brick wall forced a major strategic pivot, a move toward a data source that is infinitely more scalable, just learning from videos of humans doing stuff.
Let's just compare these two approaches for a second, because the difference in scale is just mind-blowing. On one side, you've got a $40,000 robot that needs one human operator to generate data. On the other side, a couple of cheap $75 cameras. You can just mount them on the ceiling and passively record your entire workforce day in and day out. It's not even in the same ballpark. It's a completely different economic universe.
All right, neural signal check. Let's dig into why this pivot is so important on a technical level.
So what this pivot does is create an uncapped data flywheel. And that right there is the game changer. Why? Because it completely decouples the cost of data from the cost of the robot. You're no longer tethered to expensive hardware. You can passively suck up data streams from anywhere, construction sites, farms, kitchens, you name it. And the data you collect is hardware agnostic. You can use video of a human to train a model for any kind of robot. It completely solves the cold start problem. You can build a massive data set for a new industry before you even deploy a single robot there.
Okay, but even with an infinite fire hose of data, you run into the next big problem. Robots aren't just software, they're physical machines. They have to be built. And this is where the race for AI dominance suddenly becomes a race for manufacturing dominance. The software is just one half of the equation. And this whole race is driven by a really powerful economic principle called Wright's Law. It's been around for decades, and it's simple. For every time you double the number of units you produce, your cost per unit drops by a predictable percentage. It's a self-reinforcing cycle. So in robotics, this means whoever hits massive scale first gets a cost advantage that becomes almost impossible for anyone else to catch up to. And if you look at the board today, China has a huge lead. Because of their early investments in automation and their grip on the supply chain, they have a massive advantage. We're talking a potential 12-to-1 cost gap in critical components, like actuators, the motors that act as the robot's muscles. That's not just a competitive advantage, it's a strategic choke point. It could literally determine who can afford to build and deploy robots at scale.
Okay, neural signal check. Let's reframe what this means from a high-level strategic perspective.
Here it is. Actuators are the GPUs of the robotics world. Think about it. The nation that can mass-produce the cheapest, highest-quality actuators, the muscles of these robots, is the nation that controls the physical means of AI production. That's the strategic choke point. The whole game shifts.
All right, so let's get to the final stage. We've got the data problem on its way to being solved, and we've got a hardware manufacturing race in full swing. Now, the final pieces of the puzzle, the actual breakthroughs in the AI model itself, start to fall into place. So, according to this roadmap, 3 key breakthroughs happen pretty fast. First, the models finally crack adaptive long-term memory. That's huge. It breaks the context barrier. But the real game changer, the thing that unlocks everything, is the realization that you can use video models for pre-training. This is a wild idea. Researchers figure out that generative video models have already learned an implicit model of physics just from watching internet videos. This follows Richard Sutton's bitter lesson. The methods that scale with more compute always win in the end. And what scales better than the entire internet? The internet of robotics they were looking for? It was YouTube all along. This gives the model a powerful understanding of the world before it's ever even loaded onto a robot. It enables true zero-shot performance. So when you look at the whole AGI stack, you can see how each bottleneck gets solved. The AI model's pre-training problem, solved by video models. The hardware bottleneck, solved by hitting manufacturing scale and leveraging Wright's Law. And the fine-tuning data for specific deployments, that gets solved by online reinforcement learning and the data flywheels from the robots once they're out in the world. And what you should really take away from all this is that we're seeing a fundamental shift. The strategic bottleneck for AI leadership is moving. For the next decade, it's not going to be about who has the smartest researchers or the cleverest algorithm. It's going to be about who has the industrial might to build robots at an absolutely massive scale. So with the technical path to AGI becoming this clear, the critical question for any company, for any nation really becomes, who is going to build the machine that builds the machines? To stay updated on the race to answer that question, make sure you visit us at neuralintel.org. We'll see you for the next explainer.